Hello, this is Concrete Path. We have the lecture that's capillarity in soils. So we have the groundwater, okay? The groundwater it can exist in two forms. It exists in two forms. Your groundwater exists in two forms. One of the kind is that there is gravitational water. There is gravitational water. Gravitational water. We also call it as phreatic water. Phreatic water. And second one is that we call it as capillarity capillary water, we can write capillary water. So first one is that obvious that you have that soil mass, you have the soil mass. Okay, you have the soil mass. The water is coming from because of rainfall, because of runoff. Rainfall is there, is there, and it's now going to percolate. It's going to percolate uh, to the below level of that ground. Is this if this is ground level, so it's going to percolate to the inside of that earth. Now there might be few other reasons that there would be some water that's coming because of that we call it as base flow. It would be because of base flow, maybe because of base flow also. So such that finally I would say up to this level we would be having some water, and it's we call it as we are going to call this water as your gravitational water. So this part we are going to call it as gravitational water. So what the gravitational water is there? I would say the gravitational water, the top surface here, it's actually top surface of the gravitational water is actually at atmospheric pressure. Top surface is at atmospheric pressure, and if you take any point P, pressure at that point P would be actually similar to that of hydrostatic pressure. Similar to that of hydrostatic pressure. Okay, pressure at P would be hydrostatic pressure. So that's the actual gravitational water. So here we have degree of saturation for this soil. For this soil, degree of saturation is equals to 1. So volume of air is equals to 0 in the soil mass for the gravitational water. And second one is there, that's capillary water. Capillary water. I would say if there was only gravitational force in the soil, if there was only gravitational force in the soil, if this was your soil and only gravitational force was there, so if gravitational force was only there, then finally there would have been there somewhere groundwater table was there somewhere. But I would say the soil would have been dry above the groundwater table if only gravitational force was there. If only G force was there, your soil above the groundwater table would have been dry. It must be dry, must have been dry. But if when we observe the actual scenario, when we see the actual scenario, we say that your soil is actually somewhat different. So if we have this ground level, so this is your ground level, and up to some point we are having a particular level here. One more level is there, and one more level is there, and I would say we are having one more level. Let's have one more level. So if this is your soil mass, so I would say you are having the groundwater table up to this point. Okay, this is your groundwater table. So the soil would have been, so soil above should have been that what you call as dry. Soil above should have been dry. So but we see that your soil here we have saturated soil. This soil is saturated, and this soil part of the soil is partially saturated, and this part is dry. This part is dry, but it should have been, if only gravitational force was there, this was your water table. That means this part was only what you call as this part was saturated. Here the degree of saturation was 1, volume of air equals to 0, and above we would say there is some volume of air. There is some volume of air in the dry soil, and degree of saturation is not 1. It's not 1. So we would write that. But in this case, we would say above the level, above the what you call as groundwater table, we still have soil that is saturated. We still have soil that is saturated. So we are having this water and soil is also there. So here the degree of saturation is 1. Volume of air is equals to 0. So this we are going to say this is because of this is gravitational water in the soil. Gravitational water. This part is gravitational water. What about this part? This is because of capillary action, because of capillary action. Capillary action. So what this means? That means capillary water is that water which is held above the water table against the gravitational force. So water held in soil against the gravitational force, against the gravitational force. Okay, against the gravitational force above the water table, above the groundwater table. That's because of capillary action. Because of capillary action. So, so that's your saturated. So some part of the soil, that means some part of the soil is reaching, we are having that water such that your soil becomes saturated, and some part of the soil is there that's partially saturated because of capillary action. So these two are because of capillary action. So that capillary action we can write. If you try to now, if I try to assume that your pores of the soil, if I try to assume the pores of the soil are similar to that capillary tube, similar to that of a capillary tube, then we can say what is the rise of that water, rise of water above the groundwater table because of capillary action. So we can calculate that now. If you have the concepts of fluid mechanics, you have studied that capillary effect, capillary effect. You have that container, and you are placing, let's say water level is up to this one. This is your water level, and you are placing what you call as a tube, small diameter tube. This is your tube, small diameter tube. Small diameter of that tube is there. Glass tube we can add. Glass tube is there, and it's having some diameter of d. Okay, and there is some flow. There is some rise of water in that tube because of surface tension. We have studied that surface tension sigma. So that's acting on that particular all surface along that periphery. So that's your sigma acting on that circumference, and the component of that sigma cos theta. So that's actually trying to that what you call as suck the water upwards. So there's some rise of water. There's some rise of water. That's HC. That's capillary rise. SC. That's capillary rise. So that capillary rise is given by the equation that if you have this water of gamma W, so we have that 4 sigma cos theta, 4 sigma cos theta by gamma d, cos theta by gamma d. And we say that your theta is almost the same, that our cos theta is equals to 1. Then we write general that equation 4 sigma by gamma W into d. That's your capillary rise in that tube. And similarly, if we use the same analogy, and we are going to replace that capillary tube by the pores of the soil, so we would say what is the rise of the uh, water above the water table? What is the rise of the water in the soil above the water table because of capillary action? That would be given by this equation. And if I substitute that, what you call as your sigma is equals to your sigma, that is the surface tension, that is 73 Newton per meter at what you call as, if the glass is clean, if the glass is clean and water is pure, at that time we have the equation for your capillary rise is in this way, that SC is equals to SC equals to 0.03 by d millimeters. So this is the equation for your capillary rise at this condition, when sigma is almost around 73 Newton per meter, and glass is clean, water is pure, you have the rise of the water in that tube of particular diameter d millimeters. So this is the rise of that water in meters, capillary rise. Okay, now we would say that let's talk about that sand and slit. Let's talk about sand and slit. Let's talk about the sand and slit. Let's talk about the sand and slit. For the sand, for the slit, if we substitute that, your D is equals to 0.2 effective diameter D10. If we substitute that, your D10 is there. So that's the effective size. D10 is your effective size. Effective size. If you substitute the value of diameter of that tube equals to 0.2, diameter D10 of that soil size, effective size. So our equation becomes capillary rise equals to 0.03 divided by 0.2 d10. Okay, your D10 is in millimeters and HC is in meters. So that's your capillary rise in case of sand and slit. In case of sand and slit. In case of sand and slit. Now, let's talk about what we call as let's talk about the pressure because of that capillary action. Let's talk about the pressure because of the capillary action. Let's talk about the pressure because of the capillary action. Let's say this was your tube, this was your container, and tube is there, okay, tube is there. Now this was your initial condition. I would say there is rise of water up to this level. Let's say that this is your level, final level. Up to this level, it has reached the water level has reached up to this one, such that this is your height of HSC, and this was your height of H1. This was your height of H1. I would say here at this point the at this surface your pressure is what do you call as atmospheric pressure at the surface. Atmospheric pressure at the surface. Atmospheric pressure. And above that, we would say this is your negative pressure. Can we see that this is your negative pressure? So I would say negative pressure is in the capillary zone. So important statement that we have negative pressure in the capillary zone. That's because it's water above the atmospheric level. So that's your pressure is negative. Pressure in capillary zone is negative. So let's try to draw the diagram for your pressure variation. Let's try to draw the diagram for your pressure variation. Okay, I would say that the variation would be somewhat in this way, such that the pressure here at the surface level is equals to zero. At this level, pressure would be zero, and accordingly it would vary up to this level, such that let's draw the final one. Let's draw the final one. So pressure diagram would be in this way. Pressure variation is in this way. So we have negative pressure above in the capillary zone and positive pressure that's hydrostatic pressure, positive hydrostatic pressure below the surface level. That's surface level, yeah. This value would be equal to gamma W into H1, and this value would be gamma W into HC. Gamma W into HC. Okay. Now I would say, can you tell me what is the if I use the same concept now for the soils? If I try to use the same concept in the soils, because your pore water pressure, yeah, because your pressure is it's negative in capillary zone, that means it's actually it's talking about the pore water pressure, because it is the effect of water. So we would be having the pore water pressure that's actually negative. So pore water pressure would be getting negative. If we get the pore water pressure as negative, and we say effective stress is the that total stress minus pore water pressure. If the pore water pressure is negative, that means your effective stress would be more than the total stress. Your effective stress is more than the total stress. So your what you call as your effective stress increases because of capillary action. Because of the capillary effect, because of capillary effect, your effective stress increases, and we have the equation for your shear strength of that soil. Shear strength of soil, that's related to this what you call as effective stress by the equation sigma tan phi plus c. So your shear strength also increases because of what you call as capillarity. So in the capillary zone, your shear strength increases. Your shear strength also increases. Your effective strength also increases in what you call as capillary zone. If I have this soil, if you take a general soil mass, let's say that this is your soil profile. Soil profile is there, and this is ground level. This is ground level, and there we have some dry soil up to this level, and it should have been dry. It should have been dry up to this level. That's up to this level of capital H. It should have been dry, but because of the, let's say, because of what you call as capillarity action, capillarity effect, we have some part of the soil as saturated. That means this part is saturated. Now we can write this is your HC. This is your HC. So after that, let's write that soil below that water table, that's your H2. Let's say that this is your H2. Now tell me that what is the effective stress? What is the effective stress at this level? At this level, there is a point P. What is the effective stress at the point P? We need to calculate what is the effective stress at the point P. So I would say that this soil is saturated, this soil is also saturated, and this soil is dry. So we can say that to calculate the effective stress at any point P, I would calculate what is the what you call as total stress at that point P. So what is the total stress at that point P? So total stress at that point P is actually it's actually gamma dry into height of H. Let's say this is your height of H1. We can say this is your H1. That's actually capital H minus HC. So that's actually we can write that H1 gamma D into H1. That's your total stress at that point P. And what is the pore water pressure at that point P? What is the total pore water pressure at that point P? If I have the variation that this is your capillary zone, so pressure here would have been zero. At this level groundwater table, your pressure would be zero because it is at the atmospheric level. Here the pressure is atmospheric. So, but uh, so the pressure above would be negative because of that pore water pressure in the capillary zone, that is negative pore water pressure. So the variation would be for the pore water pressure. It would be the variation that this one is your gamma W into H2, and this one is your gamma W into HC. So the pore water pressure at that point P would be negative gamma W HC, such that your at that point P effective stress at that point P now comes out to be equals to gamma D H1 minus gamma W HC. So it's greater than initial case. If there was only what you call as if there was those what you call as no capillary effect was there. If there was no capillary effect, water table was up to this level, and we had this point at a distance of h1 at a height of elevation difference of h1, and we need to calculate at this point p what is the effective stress. I would say that is actually gamma d h1 because of total stress, and because of pore water pressure it was zero pore water pressure because the variation for the pore water pressure would have been in this way, gamma wh2. So, but your pore water pressure would have been zero. So at that time, your effective stress equals to total stress, that is equals to gamma d h1. But in this case, because of the capillary effect, your effective stress got increased. Effective stress got increased by this amount of gamma WSC, gamma WSC. So, so I would say there's induced shear strength because of capillary action. So there's induced shear strength. Induced shear strength is there. Induced shear strength because of capillarity. And we have studied about the bulking of sand. We have the concept of bulking of sand. We have talked about that in the compaction of the sands. So bulking of sand is there. So what this is all about? Bulking of sand. Why this happens? We have the graph for your unit weight versus what you call as water content, and this is your dry unit weight versus water content, and we saw that there was a decrease of that unit weight at a particular value of water content in the range 4 to 5%. So what is the reason for that? Why unit weight decreases there? So actually what's happening here? So in the sand, there's in the sand there would be what you call as that capillary action. So this capillarity is because of surface tension. Do you know that? Capillarity is because of surface tension. So that's your surface tension acting on the periphery, sigma acting on the periphery, and because of that there is rise of water. So that surface tension, soil suction, surface tension, similar to that of a soil suction. Because of that surface tension or soil suction, we can lift that water amount of height h with area of the cross section as some area a, that's pi by 4d square. So that's allowing us to lift that water for that height h. So because of the capillarity, that capillarity actually is because of surface tension. We can have your particles are, if these are your solid particles, if these are your solid particles, they form a honeycombed structure. They form honeycombed structures like this one. These are your solid particles. They form those honeycomb structures. They form honeycomb structures, and that I would write solids form honeycomb structures. And we have we have a huge volume of the air. This is volume of air, volume of voids. This is the volume of voids. So volume of voids got increased. Because of that, your unit weight got decreased. Unit weight got decreased. So that's actually because of capillarity. Okay, because of the capillarity. So that's actually what's this bulking of sand related to the capillarity. So because of the surface tension, what's happening? We saw that there was that induced shear strength. That's also, we can say, this is apparent cohesion. So this is the concept of that apparent cohesion develops. Apparent cohesion develops in the sand. So what cohesion means? What cohesion means? We can see that in this concept that that's your honeycomb structure. Why these structures getting developed? Why these structures are getting developed? That is because of apparent cohesion that gets developed in the sand. Actually, in the sand, we say in the sand, actually, this is cohesionless soil. C is equals to 0. There is no interaction between the particles. There is no cohesion between the particles. So there is no interaction between the particles for your single grain structures. That's your sand. But there is a concept of apparent cohesion because of capillarity, because of surface tension, and because of this apparent cohesion, particles are coming in contact. Particles are coming in contact such that they are going to form some sort of structure that is honeycomb structure. That is honeycomb structure. So because of this honeycomb structure, we have your volume is going to get increased. That's your bulking is getting developed. Bulking of the sand. Because of that, total volume of the sand is going to increase. And you would say that you would think that your sand is so much in volume, but actually the total weight is constant, but volume has increased. Volume of the sand has increased because of this concept of uh, capillarity effect. So do you got it? So do you got it? Why this gamma d is getting decreased? So we have all those concepts getting merged together because of this capillarity effect. So let's try to revise it. That what's happening here. So we have the bulking of sand. So this is actually because of capillarity, and capillarity is because of surface tension. And because of the capillarity, what's happening? We saw that there's what you call as total stress got increased. Because of that, we have induced shear strength. Induced shear strength. Your shear strength got increased. That is sigma tan phi plus c. So that got increased. And there's one concept of induced shear strength, and apparent cohesion is there. Apparent cohesion is there for the sands. Actually, for the sand, C is 0. But because of this capillarity, there's attraction between the particles in such a way that a structure of honeycomb gets developed. And because of that, there's bulking of the sand. And so finally, we have decrease of the volume at this water content of 4 to 5%. Now, as soon as we are going to increase the water content now, let's increase the water content now greater than 5%. So your menisci are broken. That's the effect of that capillarity effect is broken. Capillarity effect is broken now. That's the effect of surface tension actually, because of surface tension. So that's getting broken. So if this was your solid particle, your surface tension, that's water is acting, that's allowing, that's resisting that, what you call as that loads, resisting those loads. But as you increase the water content, this is broken, this layer of that, this layer, because of that surface tension, the surface tension layer that was developed, that we call it as menisci, that gets broken. That gets broken, and you can now easily, what you call as, move the particles. You can easily move the particles, or you can have those close packing of the particles now, more close packing, such that your volume is decreasing, so gamma increases. Okay, that was all about what you call as capillarity in soils. Capillarity in soils. Okay, let's try to have the equation for your soils, or we can say for your general soil. We have the equation for your capillarity. This is empirical relation that capillary rise is actually equals to some constant c by wide ratio of the soil into effective diameter, effective size of that soil d10. So this is the equation that capillary rise, and where the sc is in centimeters. Yeah, Capillary rise is in centimeters. Your value of C is a constant value, and its value is in the range of 0.1 to 0.5 centimeters square. And your void ratio, we know this is the void ratio. And your effective size, that's D10, that's millimeters. We can write it in millimeters. So this is the equation for your for the calculations of what you call as that capillary rise in soils. Capillary rise in soils. Okay. So that's all about capillarity in soils, I would say. That's all about capillarity in soils. In the next lecture, we'll be talking about that problems for your effective stress versus capillarity action. We'll be having n number of problems for that. Okay,